This is Team 7's final presentation for Winter2025 design optimization, presenting the optimization of a flat pack toy glider plane. Our system is a toy glider plane with an objective to maximize range per dollar. There's three subsystems that are optimized and combined together, including the manufacturing and supply chain subsystem, the aerodynamic design subsystem, and the structure subsystem. Our system level optimization model begins with some of our parameters. We have many parameters, some of which apply to multiple subsystems, including the total gliders produced, dimensions of shipping boxes, material cost density, glider price, air density, safety factors, and thickness margin. We also have design variables, both local design variables like gliders per box, tail position, wing position, tail angle, forward velocity, and we have several global or linked design variables, including fuselage length, wingspan, horizontal tail span, and the wing shape and tail shape.
Here's an overview of our system level constraints. In general, the constraints enforce that force and moment balance is 0 for stability. The glider must fit in the box that it will be shipped in. All of its geometric shape variables must be greater than 0. It must have safety factors so that it does not experience failure during flight structurally. And then everything else is just related to, more shape variables. Our objective function is to minimize our negative lift over drag divided by our cost per plane. This essentially represents maximizing our glide distance per dollar per airplane. Some trade-offs that we see in our system: the optimizer will try to find a balance between lift and drag, structural integrity, and cost. So higher lift over drag produces longer, thinner wings, but long, thin wings have higher cost because of the higher or more material, and they're also harder to ship. And they also have structural safety factor concerns due to the larger bending moment. Some other trade-offs: packing many gliders into a box may cause the box to become too heavy and thus cost more. And also, our different manufacturing techniques are suited to higher production rates, but they are also more expensive, so there's a trade-off there as well. Here is our negative null form of our system. The formulation is MDF. There's not a lot of new information here. The most important new thing is the YC variable. So these are the variables that actually get passed between subsystems. This is our wing, tail, and fuselage thicknesses. Those are passed between the structural subsystem into the aero and the shipping subsystem. And then the lift from the aerodynamic subsystem is passed back into the structural subsystem so that it can do calculations on what the bending moment will be. So one important difference between the subsystems and when they were not coupled to the system now that it is coupled, there are variables that are now passed between each other, such as the thickness and lift. But one big change that occurred is that there's no longer a span constraint for the wings. This was in place to prevent the system or the optimizer from producing an infinite wing, but now that would be very expensive, so it no longer does that.
Our team used a combination of surrogate and analytical modeling for the different aspects of our systems. Surrogate and analytical modeling was used for aerodynamic variables and parameters. Analytical methods were used to determine structural variables and parameters. Manufacturing and supply chain was used as a surrogate model for shipping and machining costs found through research. And assumptions on material waste, shipping, and packaging were based on research as well. Infinitely thin flat plate airfoil and turbulent boundary layer measurements were found through aerodynamic and drag models. So the steps of our modeling process started with determining the parameters, design variables, and intermediate variables. Then we went to the constraints, which were defined by the USPS packaging constrictions and minimal allowable glider plane dimensions. From there, we moved on to finding the objective functions for each subsystem. And then from there, we incorporated all of these things into MATLAB. and we were able to determine the optimal parameters using certain algorithms such as genetic algorithm and Fmin-Con, as well as surrogate modeling techniques.
Our team chose to use MATLAB for this as it's a software we're all familiar with and has built-in optimization functions. A genetic algorithm through MATLAB's GA function was used for subsystems that were constrained nonlinear integer problems. GA is effective for integer optimizations, and we've used it in class before for experience. For all others, a minimization algorithm through MATLAB's Fmin-Con function was used. Fmin-Con was chosen for subsystems that were built around continuous constrained nonlinear objective functions and has also been used in class before. So to go through our optimization results, first, we're going to cover the variable names for brevity in this slideshow. I have first listed the variables along with their name and the units. This is x1 through x10. Here is x11 through x17, as well as f1, f2, f3. These three are the functions of each individual subsystem for notation, and in the final variables, we will list the whole system optimization function. So this is the first slide of the optimization results. Each row is one of the variables. This slide has x1 through x6. The columns show the input and output values for the x variables. As you can see, you have x0 run 1 and then x star run 1 repeated over 5 runs. This is slide 2 showing x7 through x12. And this is the final slide showing x13 through x17, as well as negative of fval at the end. Fval is the variable that we are optimizing for in the overall system. And since we're using Fmin-Con, we are optimizing for the negative of fval. So the values here are listed are positive and is listed as negative fval for the variable. So this is a top-down view of the final glider that we designed through the optimization model. Some things to note is that you can see it has a very long and narrow wing. This is common in high lift vehicles in real life. It also has a sort of stepped wing shape on the back. This is representative of the optimum lift over drag wing shape in real life, which is an ellipse. Aside from that, the thicknesses of each part are in line with what you would expect from a toy glider you'd purchase at the store. And the overall dimensions of this glider are also in line with optimized gliders used in competitions at the collegiate level.
For our post-optimality sensitivity analysis, we found the most sensitive constraints by the method of Lagrange multipliers at the optimal. So our most sensitive constraints had to do mostly with aerodynamics. So that was the wingspan, the moment balances, and the weight balances. This makes sense because the wing wants to be really long and also produce a lot of lift. But for our sensitive parameters, we decided to analyze all of them. And out of all of the parameters, the dynamic viscosity of air was the greatest by far. This makes sense because it has large knock-on effects on the structure of the gliders, which also has effects on how many we could produce and which influence how much they cost. Some other things that influence the cost were the machine cut rate and the thickness margin. The thickness margin is how much room the wing has on the top and bottom of the fuselage, so it can like slide in. Obviously, more thickness margin means more material, which is more costly. If you go to the next slide, we could see some examples of what the glider will look like under different effects. So for instance, if denser balsa wood was used like on the left, you'd have a much thinner wing. But if you have change some of the variables of the air, such as the density or the viscosity, you could see that the sort of the shape of the wing changes, but also the locations of where the wing is or where the stabilizer is also move around.
To reality check our results, we compared our optimized glider to a glider Daniel designed in the Aero 740 aerodynamic design course, which he also built and tested empirically. Only one of these gliders pictured on the right was built, with a supply chain cost of 58 cents solely for the balsa wood and glue used. The glider achieved an L/D of 6.5, which is less than the optimized 12.88 that we predict. Daniel's glider was significantly lighter, but the objective function was lower due to the lower L/D and higher cost. There is a bit of a discrepancy here in that for the ME555 glider, we are producing in bulk, so the dollars per gram of the material is actually much less, which allows the glider to weigh more and allows structural trade-offs to have a higher L/D with a higher weight glider. There were additional constraints in the built glider for the aerodynamic design course as well, such as a fixed wing and tail span and spacing, while these variables are free to be optimized in this course. Overall, the values from the Aero 740 glider and the optimized ME 555 glider are on the same order and make sense in terms of what could be expected for this type of project. Comparing the subsystem values of the interim report to the optimized solutions of the final report, we see that cost went down per aircraft because in the interim report there were assumptions made because there was no coupling about the size of the aircraft. Since the aircraft is thinner and smaller than predicted at the interim report, the supply chain cost is less. The lift over drag, or the range, went up from the interim report to the final report because mostly the aerodynamics model was improved to take better advantage of span efficiency, which is the nonlinear taper effect that you see on the wing planform. The mass went down partly because of the aerodynamic improvements, but also due to the coupling of the structural and aerodynamic subsystems. For the interim report, a certain dimension of the aircraft was assumed, which was actually larger than the final optimized size of the aircraft, which allows the mass to be lower. With the lower cost, higher L over D, and lower mass, the optimized objective function is much higher than the individual objective functions from the interim report. This is mostly because of the assumptions that were made for the coupling that were resolved in the final report. Overall, we found that decreasing the system cost and mass increased the efficiency, and improving aerodynamics results in a reduction in air resistance and improved speed, and that the machine cost and machine time balance each other pretty closely, so neither of the manufacturing techniques were significantly better. Some potential improvements could be using a vortex lattice code, which is a higher fidelity aerodynamics code than what we use to compute the lift and drag. There are differential vortex lattice codes that exist, just not in MATLAB. And adding support for additional manufacturing methods or different methods for different components, or considering other materials such as foam with carbon reinforcements, which might be more durable and more cost-effective to produce at scale. This concludes our presentation. Thank you.